All right, section 4.2, we're going to start out by doing a little review from pre-calculus, and we're talking about sigma notation. We're going to be able to use sigma notation to write and evaluate a sum of numbers. And we're also going to work with finding the limit of a summation. So the first thing we're going to do is review what sigma notation is. Remember, the sigma notation has this big E, stands for sum. And then we're going to have a lower bound, which is x equals 1. That's going to tell us what number we're going to start with. We're going to have an upper bound. It's going to tell us what number we're going to stop with. And we're going to take the lower bound, plugging it in for our variable. And we're going to increase in increments of integer values. So 1, 2, 3, 4, 5, 6, all the way up until we get to this upper sum. Then we're going to add those answers together. So if I take 1 and plug it in, I get 3. I'm going to go to the next integer value, which is 2. 2 plus 2 gives me 4. Next integer value is 3. 3 plus 2 gives us 5. And then 4 plus 2 gives us 6. And we stop because we plugged in our 4, our upper boundary. So we take 3 plus 4 plus 5 plus 6, and it gives us 18. We can do this with any variable, and we can start any number and we can end at any number. So our lower and our upper bound can be whatever we want, and our variable can be whatever we want as long as they're the same. So as long as our variables are the same here that we start with and what our equation is in. So if I plug in 3, I get 9. If I plug in 4, I get 16. 5 is 25, and 6 is 36. So 9 and 16 is 25, 50, 86 would be our summation. Again, that should be reviewed from algebra or from pre-calculus. We also spent some time writing a sum in sigma notation. So it doesn't matter what variable we have that we start with. We can do x, we can do n, doesn't matter. In this case, we're looking for a relationship between our denominators and our numerators, or in our terms here, essentially. So if I notice I have 1 in my numerator for each one of them, I go from 2 to 4 to 6 to 8 to 10. That's a linear function, isn't it? 2, 4, 6, 8, 10. And that is 2n, or 2x in this case. We can write this as 2 times 1, and 2 times 2, and 2 times 3, and 2 times 4, and 2 times 5. Or you can think of it as a linear equation, which would then give us 2 times the x value, or our term. And where do we stop? Well, if we plug in 1, we get 2 times 1 is 2, 2, 3, 4, 5. We're going to stop at 5. If you take your upper bound minus your lower bound plus 1, that'll give you the number of terms that we have. That was something that I showed you last year as well. We have 2, 6, 12, 20, 30, 42. This is not a linear equation because we can't go from 2 to 6 and 6 to 12 with the same increase. So we got to think of something else to do with that one. So here, just to show you that we can, we're going to change the variable to n. So how do we get from 2 to 6, 6 to 12, and so on and so forth? Again, think of this as our first term, second term, third term, fourth, fifth, and sixth term. If I think of that, I think of 2 times 1, and then 3 times 2, and 4 times 3, and 5 times 4, and 6 times 5, and 7 times 6, where my number term is here. And most of these, if you base it off of the term, you'll generally be able to get to that equation. So I take the number term, so n, and then 2, 3, 4, 5, 6, 7, that's just one more than the number term that we have. So n plus 1, to where I stop when n equals 6. You could, if you want, multiply it out and you get n squared plus n. There are other ways that you can go about finding that equation. It is a quadratic equation. The reason that we know it's a quadratic, if we go 2 to 6 to 12 to 20 to 30 to 42, if I look at the difference, I have 4, 6, 8, 10, 12. And if I look at the differences of the differences, so 2, 2, 2, 2, that's going to tell us that we have that quadratic, that exponential equation there. All right, so write the sum using sigma notation. Here I have 2/3 plus 3/4 plus 4/5 plus dot 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 dot. plus 8 over n. So we don't know how many terms are in here. It's just saying that this pattern is going to continue. So essentially, I'm looking at these first 3 terms to tell me what my expression is. That's a bad looking sigma, isn't it? Well, here if I have, it looks like I'm just increasing by 1, and here I'm increasing by 1 in the denominator. But I start at 2, and here I start at 3. So I can go ahead and start, my first term is 1, but I could have n plus 1 on the top. Since my first term was 1, 1 plus 1 gives me 2, 2 plus 1 gives me 3, 3 plus 1 gives me 4, so on and so forth. And in the denominator, if I'm going to add, if I start at 1, I'd have to actually start with 2 plus the term. So 2 plus 1 gives me 3, 3 plus 1 gives me 4. So here I'd have n plus 2. And I'm going to stop, but what do I stop with? If I plug 1, or what number do I plug into here for n in order to stop at 8/9? And that would be the number 7. How about limits? Oh, we so enjoyed limits, didn't we? Let's find the limit as n goes to infinity of 15 over n to the third times n minus 1 squared over 3. Thing we need to recall about limits going to infinity and a fraction. Remember that the leading term tells us what's going to happen with the numerator and what's going to happen with our denominator. So we could multiply all this out. And if we multiplied it out, we'd have n times n minus 1 times n minus 1 times 15 for our numerator. And then we would have 15n squared minus 15n. And to that we'd have multiplied by n minus 1. Multiplying that out, we get 15n to the third. Minus 15. Let's see, minus 15n squared, minus 30 n squared. And then we have a plus 15n. And that would be it, wouldn't it? I feel like I missed something. Nope, it was 15n. So, anyway, remember that this extra stuff here doesn't tell us anything about how the function is going to end when n goes to infinity. It's only this leading term here. So if we think about where 15n to the third came from, come back down here, we have 15, right here, 15, we have our n. We multiply it to this n here, that gives us 15n squared. We multiply it to the n here, which is 15n to the third. So if we kind of get rid of this extra stuff in this binomial, if we get rid of this minus 1 here, notice we'd have 15 times n squared, or 15n to the third. That would eliminate all of this extra stuff in here, and we wouldn't have to worry about any of this stuff occurring. In our denominator, we have 3n to the third as well. So we're looking at the limit as n goes to infinity of 15n to the third over 3n to the third, which is 5. So the limit as n goes to infinity of that gives us 5 as our answer. We're going to do another one of those, just kind of a little shorthand though, a little shorter. We're looking here as n goes to infinity of 30 times all of this, so divided by 2, n to the fourth times our 5. So again, I'm going to eliminate this extra stuff in here, because again, that's not going to matter as n gets larger and larger and larger. So I have 30 and n times 2n times 2, which gives us 2n to the fourth. And on the bottom, we have 2n to the fourth times 5. And it's not always going to happen this way, but notice our 2n to the fourths, they're going to cancel each other out. So if I take the limit as n goes to infinity of 30 over 5, that gives me 6 as our limit. So why do we do this? Well, we're going to kind of mesh all of this together here very shortly. The first thing I want you to do is go ahead and find the summation from 1 to 3 of 2. What does that mean? We're going to plug 1 in for our x's. Notice there's no x there. So I have 2. And to that I'm going to add 1 to my integers here. If I plug in 2, I still get 2. If I plug in 3, I get 2. So I get 2 plus 2 plus 2, which is 6. Here, if I go 20 times, summation of 3 from 1 to 20, I get 3 plus 3 plus 3 plus 3. They're always going to be the same until I get my 20th term. So I get 3 times 20, which gives me 60. Here, if I go out to 4, out to n terms. So if I have 4 plus 4 plus 4 plus 4, all the way out until I get n terms, I'm going to have 4 times however many terms that is, or 4n. More generalized, if I go from 1 to n of any constant, doesn't matter what the constant is, if I go out n times, the summation is going to be c times n. And that's one of our summation rules. The summation of a constant from 1 to any number is going to be that constant times our upper bound. All right, another rule that we want to look at, if I go from 1 to 4 of x, so if I have 1 plus 2 plus 3 plus 4, that's going to give me 10. If I go from 1 to 10 of x, that gives me 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8, 9, and 10. Well, I could probably add those up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Adding those together, I get 55. What happens though if I get from 1 to 100? Now that this number gets very large, it's now going to be very complicated and ugly for me. So can we come up with a way of maybe getting to this without having to write out 1 through 100? Recall up here we had 1, 2, 3, and 4 and added to give us 10. If I take this 4 and this 1 and this 2 and this 3, add them together, I get 5 and 5. 5 plus 5 gives me 10. Over here, 1 plus 10 gives me an 11. 2 and 9 gives me 11. 3 and 8 gives me 11. 4 and 7 gives me 11. And 5 and 6 gives me 11. So I had 1, 2, 3, 4. I had 5 11s. So 5 times 11 gives me 55. So here I had 2 times 5 gave me 10. Well, what do I know about 2 and 5 with my summations? 2 is half of 4 and 5 is half of 10. So if I take half of that number, 1/2 of that 100, and I multiply it to the sum of the first and the last term. So in this case, I have 100 would be my last term. My first term would be 1, so I'd have 101. So I'd have half of 100 times 101. If you want in your calculator, you could do that, but we'd have 50 times 101, and that's going to give us 5,050. What happens if we take from 1 to any number and we take it of I? So if we go from 1 to 2 to 3 to 4, how can we get that in general? Well, how do we get this over here? We took 1/2 of the upper bound, so our n value, and we multiplied it by 1 plus that upper bound, the nth term. So we get 1/2 of n times 1 plus n. And that's going to lead us then into some formulas that we need to know and recognize. And we saw these last year in pre-calculus as well. So if I had the sum from 1 to n of any constant, it equals the constant times n. If I go from 1 to n of any I, so any expression I, where I is what we start with, then we have n times n plus 1 over 2. If it happens that we're I squared from 1 to n, then we have n times n plus 1 times 2n plus 1 over 6. And to the third is n squared times n plus 1 squared over 4. These are generally the ones that we are going to use, the ones we studied last year. That's why, because we're going to study them again this year. So we're going to put it now together, the derivatives, the summation rules, and we'll put it all together to be able to find the limit as n goes to infinity of a summation. So limit as n goes to infinity of a summation, To start with, we should realize that we know the summation when I equals 1 to n of some value. We just found that up here. This n squared is going to be a constant. So we could rewrite this as the limit as n goes to infinity of 1 over n squared times the summation of I equals 1 to n of 8i. 8i, that 8 actually could come out in front as well because it's a constant. So now we just have the summation from 1 to n of I. We know this summation. That summation is n times n plus 1 over 2. So we can rewrite this as the limit as n goes to infinity of 8 over n squared times n plus 1 over 2. And that's going to look very familiar to us because we just did it a few minutes ago. So to clean this up, we can get rid of, again, this plus 1. Doesn't make any sense to us because it's not going to affect it. It's going to make sense to us, but it's not going to make any difference in our final equation. So I have 8 times n, which is 8n squared, over 2n squared. And that's going to reduce to 4. And that'll be our summation of this, or the limitation of this summation. I have one last one to play around with. Again, I have a summation. I have 3i squared over n to the third, and it's going to infinity. So I can rewrite this as the limit as n goes to infinity. I can bring out the 3 and the n to the third, because they're not going to change. Only the I is changing. Times the summation from I equals 1 to n of I squared. I just happen to know this summation as I goes from 1 to n of I squared, and that's going to give us 3 over n to the third times n times, getting ahead of myself, n plus 1 times 2n plus 1 over 6. That should be an n there. Again, to find this limit now, we can get rid of the plus 1 and the plus 1 here because they're not going to have any bearing on the final limit. So we have 3, we have n times 2n, so we have 3 times 2n to the third over 6n to the third. 3 times 2 gives me my 6. N to the thirds are going to cancel. 6 divided by 6, that's going to give me 1. And that's going to give us our summation, or our limitation of that summation. So we are going to put all this together, and we're going to put it in with areas very soon, probably tomorrow, so you can see exactly how this is going to allow us to find the actual area of a region under a curve. So good luck, enjoy, and happy limiting.